Welcome to today's paper reading. Today's paper is titled, Lessons from the Trenches on Reproducible Evaluation of Language Models. This paper was published on the AR14 preprint by Stella Biderman and colleagues from Illither AI, Stability AI, and MBZU AI. The abstract highlights the ongoing challenges in evaluating language models within NLP. These challenges include the sensitivity of models to their evaluation setup, the difficulty in making proper comparisons across different methods, and the lack of reproducibility and transparency in research. Drawing from 3 years of experience, the authors provide an overview of these common challenges and delineate best practices to address or mitigate their impact on research. Additionally, the authors introduced the Language Model Evaluation Harness, LM-Eval, an open-source library designed to facilitate independent, reproducible, and extensible evaluations of language models. This library aims to tackle the aforementioned issues and includes features that support its use in alleviating methodological concerns, as demonstrated through case studies. In the machine learning and language modeling communities, benchmark evaluations are essential for tracking progress and demonstrating improvements in new methods. However, inconsistencies in evaluation practices can lead to skewed performance comparisons, potentially influencing future research directions. Transparent and reproducible evaluation of large language models is particularly challenging. To address these issues, the Language Model Evaluation Harness was developed to provide a flexible evaluation library, enabling researchers to easily run benchmarks on any model and connect new models to the broader ecosystem. The primary challenge in evaluating language models is what the authors term the key problem. This problem arises from the fact that there can be many semantically equivalent sentences that are expressed in syntactically different ways. Ideally, we would have an automated method to detect when two sentences convey the same meaning but use different words. However, the best tools we currently have for determining semantic equivalence are the language models themselves, which creates a circular dependency. This issue significantly impacts the approaches taken to evaluate these models, necessitating robust methods that balance accuracy and efficiency. The evaluation of language models, LMs, faces significant challenges due to the lack of a one-size-fits-all solution. One approach to solving this is using expert human annotators to score model responses for correctness. However, this method is not widely adopted due to its high cost, which includes fair compensation for annotators, making it prohibitive for smaller organizations. Additionally, relying solely on human assessments must be done with caution as they can be flawed and biased, particularly in complex judgments like factuality. These issues highlight the need for careful consideration and alternative methods in LM evaluation. The Language Model Evaluation Harness addresses the high costs of manual human evaluation by utilizing automated metrics. These metrics offer notable advantages such as being fully reproducible, easier and cheaper to compute, and avoiding some issues faced by human studies. Model-based metrics, which leverage large language models as graders, have gained momentum as proxies for human preference evaluation but are known to have flaws and reproducibility issues. Implementation details are crucial as even minor variations in prompts or formatting can significantly impact the performance and validity of evaluations. Without access to the original evaluation code, it is nearly impossible to account for all the subtle details that can affect outcomes, leading to potential inconsistencies and difficulties in fair comparisons across different implementations. Figure 1 illustrates the timeline of the release dates for several prominent language model, LM, benchmarks in comparison to key shifts in LM evaluation practices represented by the releases of BERT, GPT-2, GPT-3, and ChatGPT. This timeline highlights how many benchmarks were designed before significant shifts in LM usage, such as in-context learning and chat interaction, which were not initially considered in their design. Consequently, the current evaluation practices for autoregressive LMs often differ from the original methods described for these benchmarks, with the exceptions of MLU and math. This divergence can impact the validity and difficulty of the evaluations in ways that were not foreseen. Figure 2 illustrates the operations performed by a task object within the LM-Eval framework. The tasks are configured either through YAML files or as Python subclasses. They include a data source utilizing the dataset's library, tools for defining prompts and their formats, mapping these prompts to rendered inputs and expected output types from a language model in the form of requests, and rules for post-processing the language model's outputs and calculating the final task metrics. Figure 3 provides an overview of the 3 core request types supported by our evaluation framework. These include 1. Conditional log likelihoods, which compute the probability of given output strings conditioned on some input. 2. Perplexities, which measure the average log likelihood or probability of producing the tokens in a given dataset. And 3. Generation-based requests, which generate text until a given stopping condition is reached from a model conditioned on some input. In this section, we explore the impact of different prompts on evaluation results, highlighting the collaboration with the Big Science Workshop and the integration of the prompt source library. We also discuss the sensitivity of scores to the specifics of the evaluation setup, using the ARC and MMLU benchmarks as examples. Finally, we present a comparison of zero-shot model performance across various setups, noting the scores and standard errors for models like GPT-Neo X20B, Llama 2-7B, Falcon 7B, Mistral 7B, and Mixtral 8X7B. Table 1 presents a comparison of zero-shot model performance for several pre-trained language models on the ARC Challenge subset and MMLU benchmarks. The evaluation is conducted across 2 commonly used prompt styles, close and MMLU style. The table reports on normalized accuracy, along with 95% confidence intervals calculated via the standard error of the mean. This data helps in understanding the performance variability of different models under various prompt conditions. Figure 4 illustrates the use of LM-eval to investigate how different prompts affect model performance, as documented by Muennighoff et al., 2022. Each dot in the figure corresponds to a different prompt, and the histograms provide a summary of the performance variations induced by these prompts. Similar analyses can be found in studies by Workshop et al., 2023, and San et al., 2022, among others. In this conclusion, the authors highlight several challenges in language model (LM) evaluation. One major issue is the difficulty in reliably comparing model performance due to variations in evaluation setups. The authors emphasize the importance of full disclosure of evaluation methods to ensure meaningful comparisons. To address these challenges, they introduced the LM-eval library, which is designed to enable easier and more reproducible benchmarking. This library supports configurable task design and encourages community contributions, aiming to improve the rigor and understanding of LM evaluations. The authors hope that LM-eval will foster a more interoperable ecosystem and promote better communication among researchers. Thank you for watching.